All right. Quiet, please. Thank you. Homework question. So what were you asked to do? The question was to produce a linear programming formulation. So that's something that's similar to what we did in the chess set problem. Okay, and so in this case, we're not making chess sets. What we're making is telescopes, and they also need some resources. So it's this kind of prototypical question that can appear in linear programming, and the solution always has three parts when you're doing a linear programming formulation. What are the three parts? You should know by now. What are the three parts? Speak up. Decision variables and constraints and objective. Yes, brilliant. Okay, so the decision variables, I've put three. I call them x1, x2, and x3 because I'm being boring. But what are the decision variables in this problem? I'll just tell you because I'm getting bored. Okay, so x1 can be the number of Newton telescopes made per week. Okay. Now we know what x1 is, then it's not very hard to figure out what x2 and x3 are going to be. So x2 is the number of Hubble telescopes made per week, and x3 is the number of astrograph telescopes made per week. Okay. Now, some people I know of have proposed putting the number of hours in the optics department as a decision variable. Now, that doesn't work. If instead of these three decision variables, you'd put the number of hours in optics, the number of hours in mirrors, and the number of hours in assembly, it just, you'd really struggle to get the formulation correctly. It just doesn't work. Okay, so the decisions you're making are how many Newton telescopes to produce, how many Hubble telescopes to produce, how many astrograph telescopes to produce. The rest follows. Okay, once you know how many Newton, Hubble, and astrograph you're producing, you know how many hours you'll need in optics, because you times the number of Newtons by 2, you add the number of Hubbles and the number of astrographs based on the table, and you get the number of hours you need in optics. So the decision variables in such simple cases, they have to be like that. There's basically no way around it. Oh, and the objective, where's the objective? Well, it gives it away here, maximizes the total profit. So I've already put maximize. Now the total profit, well, the profit is given here somewhere, isn't it? So £40 for each Newton, £50 for each Hubble, and £60 for each astrograph. So altogether, it's like this. Okay, if you're making x1 Newtons, then the profit of all your Newtons is going to be 40 times x1. And then to that you add the profit of the other one and the profit of the third one. And you can put the unit of the profit, which makes the interpretation at the end, as we'll see later today, easier. Okay, and the constraints are like this, because why? Well, because this is, as I just said, this is going to be the number of hours you need in the optics, I think, and the number of hours per week in the optics. So we should put here hours per week. The number of hours per week available in the optics department is 40, and the same for the other two departments. Okay, and don't forget the non-negativity. If you don't put the non-negativity there with something like this, with a problem like this, then you're in trouble again, because in some cases, the optimal solution would then try to decrease the number of something that's not very profitable below zero, in order to be able to produce more of the thing that is more profitable. Okay, so if you don't have the non-negativity, you can get solutions with negative variables, and that has no interpretation in this case. Any questions about this homework exercise? Any objections? Better solutions? No? Okay, so that you can again self-mark your homework solution and put a 0 or a 1 in the homework solution column. Thank you. Now, okay, last week we were doing the chess set problem. What is a chess set? I didn't tell you last week what a chess set is, but it's this. Okay, this is a chess set. And production of chess sets needs some wood. Well, I hope everybody knows what wood is. And you also need some time on lathes. And I didn't tell you what a lathe was last week, so this is a lathe. You'd probably quit my job and work with something like that. It could be more fun. Oh no, this is enough fun. So we had this last week, and what it led to was this formulation. So with two decision variables, an objective, and 5 constraints. Yeah, can you see 5 constraints? Okay. I was hoping someone would say, oh no, there are only 3 constraints. But there are actually 3 what I call functional constraints, so the top 3, and then there are the 2 constraints that both x1 and x2 have to be greater than or equal to 0. Now, how do we solve a problem like this? I told you, I promised you 2 methods, and I haven't given you one yet. Well, any one of them. And the first one is to draw a picture. Okay, so I'm starting to draw a picture. It looks like this. It doesn't fit. Now it fits. So I take advantage of the fact that we only have 2 decision variables, and I can draw a picture in the plane. And I can put x1, one of the decision variables, on the horizontal axis, and x2, the other decision variable, on the vertical axis. And now, what I want to do is try to find all the points in the plane with coordinates x1, x2 that satisfy all these constraints. Okay, so how do I do that? Well, start with this constraint. So this is the first constraint. How do I find all the points in the plane whose coordinates satisfy this inequality? What is it going to be? You should know that from A levels, hopefully, or some such. So where are the points going? Where are they going to be in the plane? With one word. One word. It will be a half plane. Have you heard the word half plane before? Where's the education system going? Students come to university not knowing what a half plane is. Okay, so I'll tell you what a half plane is then. A half plane is you draw a line, a straight line, and everything on the one side of the line is a half plane, including that line. Okay? So which straight line do I want to draw? I want to draw a straight line which has equation 3x1 plus 2x2 is equal to 160. Okay, that's a straight line. Hopefully everybody knows that at least. So how do I find this straight line? Okay, so a straight line, if you want a straight line, it's enough if you find 2 points on that line. Okay, so the easiest 2 points is, well, if I make x1 0, then x2 has to be 80. So a point with coordinates 0 and 80 is going to be on this straight line. So this is that point here. And the second point, I can put, oh dear, 160 divided by 3. Well, maybe I didn't pick the best point. I'll do a different one. So if I put x2 to 5, I get x1 50. Does that work? Aha, now we've locked you out. We should keep this sector free for those who come late. Okay. Do you agree with me that these 2 points satisfy this equation? Yeah? Okay. Am I being too slow? Okay. 55. That's here. So I've got these 2 points. I can draw a straight line through these 2 points. Okay, and if I want all the points that satisfy this with the inequality, less than or equal, then that is all the points on one side of this line. Is it to the left or to the right of this line? Left. Why? Well, yes. Not quite. I mean, it's not so easy, but I mean, it is so easy. But okay, it is but it's not quite right. But yes, but it is a little bit right. Perhaps a better way to find out is where you pick some point here and test it. So for example, the point with coordinate 0, 0, if I put it there, then it satisfies it. So it has to be in the half plane. So this half plane to the left here. Oh, I should be doing it in green. I don't know what should I begin here? Yeah. So here on this side of this straight line, all the half plane, all the way, including the sofa, those points satisfy this inequality. Okay? Now, quicker for the rest of them. So the next, so this is, I'll put it here somewhere. So this is the straight line that says 3x1 that has equation 3x1 plus 2x2 equal 160. Then the next one was x1 plus 4x2 is less than or equal to 200. So equal to 200. So I've got 2 points again. One is 0, 50, and another one is 40, 40. So 0, 50, that is here. 40, 40. That is here. Straight line. So this is x1 plus 4x2 equals 200 is a straight line, and I want less than or equal to, so that's going to be all the points on this side of the straight line. And the next constraint was 1/2 x1 plus 1/2 x2 is less than or equal to 31. So that is 62, 0, and 0, 62. So point thereabouts. And there. And I draw the straight line. Okay, I'm going to put it 1/2 x1 plus 1/2 x2 equals 31. And I want to be on this side. Does it make sense? Okay, I have 2 remaining constraints because I said there were 5. So the 2 remaining constraints is that x1 is greater than or equal to 0, and x2 is greater than or equal to 0. Now, x1 is greater than or equal to 0. I already have that line there. This one, and the other one is this axis. Okay, so they're already there, but I have to be on this side and on this side of these 2 lines. So now, where are the points that satisfy all the constraints? I know everyone's sleepy after lunch. I'm also sleepy after lunch. Give me something. Say a word. Pardon? None. None. Are you sure? So for example, this point, 2020, does it satisfy all the constraints? Yes, it's on the right side of each of the lines, each of the 5 lines. So the intersection of all these half planes is this polygon. I'll mark it green. Okay. And this polygon contains all the points whose coordinates satisfy all the 5 inequalities. So in linear programming, does it look green? Or is it trying in vain to make it look green? It's green. So in linear programming, that polygon is called the feasible region. Okay, so the feasible region is the set of all points, well, in the plane in this case, where there are two decision variables, which satisfy all the constraints. And each of them is called a feasible solution. That's the terminology. So should be writing it somewhere. Right? So, each point x1, x2, that satisfies all the constraints is called a feasible solution. Have we solved the problem? No. Why not? What's missing? The profit line. What is the profit line? P equals, aha. That's an interesting suggestion. So Spiridon is proposing a profit line. Okay. P equals 15x1 plus 20x2. But what is P? But what is the profit? We don't know. So I don't know whether, well, I've never heard the word profit line, so it might be used, but I don't know. But yes, that's the objective function, but the objective function is not a line, so it's kind of, you know. So what exactly are we doing? Okay, but at the same time, there is something with a line, because if you fix profit P to be, I don't know, 300, okay? So if you say P is 300, then you get a line where there is exactly the equation 15x1 plus 20x2 equals 300. And that's going to be a straight line. Okay, I'll draw it. So I need 2 points on that line. So this is one. This is another. I'll draw a straight line. And this is a line with equation 15x1 plus 20x2 equals 300. Okay, so what does that mean? Well, that means that if you pick any point on this line, that's also in the feasible region, so including the endpoints of the line segment, the whole line segment, including its endpoint, and you look at its coordinates. For example, you'll get to the point 10, 7.5, or something like this. So if you're producing 10 small sets per week and 7.5 large sets per week, whatever that means, you will be making £300 per week. Okay, so no matter, but that's true for any point on this line. Does that make sense? So anywhere on this line, you could, in this line segment, you could do your production plan, this many small sets, as many as the x1 coordinate of that point, and this many large sets, as many as the x2 coordinate of this point, and you'll be making £300 per week. You with me? Good. Now, is that the best you can do? Well, no, because you could move this line to here, for example, 30, 40. Like this. So this line has the equation 15x1 plus 20x2 equals 600. And so again, what you can do is pick any point on this line segment, for example, 30, what is it? 15, okay. Start producing 30 small sets, 15 large sets, and be earning £600, I think, yeah, £600 per week. Does that make sense? Is that the best you can do? No. What can you do? You keep moving the line up and to the right. Well, how long can you go with that line up and to the right? Until you reach the first one. Aha. So if I'm going like this, like this, like this, like this, at some point, if I draw a line, I'm lost. If I draw a line through 80 and 60, like this, okay, that's a brilliant line because it has the equation 15x1 plus 20x2 equals 1200. So any point on this line gives me a profit of £1,200 per week. Now the problem is, I don't have any feasible solutions on that line, do I? Because no point on this line is in the polytope. Okay, so I can't make profit of £1,200. But I can do a line that is parallel to this one, and is to the most top right of all lines parallel to this one, but still has some intersection with the feasible region. And this intersection is, in this case, just this one point. And I would like to say that this point is an optimal solution to our problem. Do you agree? I'm doing it in a very suggestive way, so you're kind of bound to agree almost. But in fact, in this case, exceptionally, I'm not kidding. So it actually is the optimal solution. So no joke there. Okay, but that's good enough. Now, what are the coordinates of this point? Oh, yes, that's a brilliant idea indeed, yes. So if you want to find out, I mean, you could start looking at whether you can actually see something down here or left there or so on. But that wouldn't be quite so precise. But if you want the precise coordinates, then, well, here's the intersection of two lines whose equations we know. So to find the coordinates of the optimal solution, well, the optimal solution satisfies x1 plus 4x2 equals 200. Yeah, because it's on this line. And it's also on this line, which has this equation. So it also satisfies half of x1 plus half of x2 equals 31. So if you, oh, it doesn't show, sorry. So if you solve this system, what you get is, what do you get? Have you got it yet? But x1 is 16 and x2 is 46. Is that right? Thank you. Got lost in my notes for a short while. It's because I always try to recreate everything. Okay, and then therefore the profit is, it's what is it? 15 times the first plus 20 times the second. Who invented this example? $11.60. Because at 15 times x1 plus 20 times x2, it should be 11.60. Okay, are you happy with this? I'm kind of happy as well, but not quite. Okay, so what's the phase that comes after you've solved the model in an OR problem? Yes. Implement it. So for the implementation, you want to give some kind of interpretation of what you found. So you won't really be implementing it in practice as such, but we should at least give the conclusion of what we found. What have we found? Okay, so we found that the optimal production plan is to produce how many small sets? Yeah, 16 small sets and 46 large sets per week. The weekly profit will be £1,160. Can we say anything else? For example, will there be any spare boxwood? Yes? No? No, why not?
Because when you've got chess sets you just made into the inequality, it says that 16 kilograms of small sets is 4 times 46 sets of large sets.
Yes. So I'll say that again, just in case So the amount of box wool that we need is given by x1 plus 4x2. And if we plug in the solution, x1 is 16 and x2 is 46, and we get 16 plus 184, which is 200, which is exactly the amount of boxwood available. So there won't be any spare boxwood. And from the picture we can tell, because the optimal solution lies on this straight line. Okay, and this straight line is the line of all the solutions which are using exactly all the boxwood. And in the same way, we can see that all of the finisher time is going to be used up. But we can see here that not all the lathe time is going to be used. So there will be some spare lathe time because the optimal solution is not in this constraint boundary. Okay, so so from this we can see that all the boxwood and finisher time will be used. But there will be spare time on the lathes. And if you want to know how much, then you just plug in 16 and 46 into the formula for the number of lathe hours and you get it. But it's not, yeah, so that's simple, so let's not do it. Okay, so just some fun questions. Okay, fun questions. Now it's the fun question. Well, there will be fun for me. Okay, question number one. Is it true that in any linear programming problem with two decision variables, say, any optimal solution you find will always be in the corner of the polytope, or in a corner of the polytope? Understand the question? Is it so? We found an optimal solution. There's only one optimal solution, obviously, and it's in a corner. It's in a vertex of the polygon. Is it true that any optimal solution ever will always be in a corner? No? Why not?
The line parallel to the line between 2 points of any point on that line between 2 corners.
Yes, brilliant. So if, say it again. Where's my, no. If the profit line happened to be parallel with this constraint, okay? Well, you call it the profit line. I'll start calling it profit line. Then what you get is the last line that has non-empty intersection with the feasible region is that same line as the constraint boundary. Okay, so then in that case, all the points on this segment would be optimal solutions. So there will be many optimal solutions in a situation like that. Okay, that was a fun question. Question 2. Is always at least one optimal solution in a corner? No? Yeah? So who's for no? Who's for yes? It ended 1-1 with oh no, 1-2 with about 200 abstentions. No, it's not 200 people, is it? Okay, so the answer is yes. Well, yes. So if there is an optimal solution, then there always is at least one optimal solution that's in a corner. Okay, so So if you don't want to do this kind of shifting the line operation, where you're bound to make some errors, then what you could do is simply evaluate the objective in all the vertices, in all the corners of the polygon, and compare the values there. And the best one that you find in the corners is going to be the optimal solution. And if you find that two corners have the same value, then you can see that all the points between the two also are optimal solutions. Okay. Question 3. What do I want? Is there always an optimal solution? No? Yes? So when is there not an optimal solution? No? We don't quite, well, that would mean that they're parallel, but that doesn't, when the objective function is everywhere. The objective function is a function that takes any point in the plane and gives you a value. Okay, so it works everywhere. That's so you can't. So no. But good ideas. I like good ideas, even if they're false. If there's no feasible region, yes, that's a good observation. So we don't say that there is no feasible region. We say that the feasible region is empty, but the idea is the same. So if you manage to get constraints, and believe me, it's possible. I'll just do a rough sketch. So if you do a feasible region, okay, you have to be. So you have to be there and there and there and. No, what am I doing? And there. Now there's still a feasible region. No. And there, and there, and I'll kill it now. And there. And there is nothing in the feasible region. Okay, that's a stupid example, but you get the idea. If they don't intersect all the half planes, then there is no there are no feasible solutions, and yeah, therefore there's no optimal solution. There is a second situation when there is no optimal solution, and that is when constraints could look something like this. Okay, so you have to be there, and this feasible region goes to infinity, and for some objective functions, you can make your objective value as large as you want. So there is no optimal solution because you can go to infinity. Okay, so we'll be talking about that later as well. Now, the most important question is question 3. What do you do if you don't have 2 decision variables but 4? Now, well, you're working in the plane because you have 2 decision variables. Okay, so maybe if you have 3 decision variables, if you really tried hard, you could build a 3-dimensional model. But if you have 4 decision variables, then you're in trouble. Okay, so that's one disadvantage of this method. Also, it's easy to make errors because you draw it wrong. So it's Precision, I'll write precision. Question mark, because you don't know how precise your drawing is. You know, that's a problem. Especially with me, it's a problem. So I'm quite chuffed with my picture. And so on. So this method is nice because it shows us what linear programming is about. Okay, you get a feasible region, which is defined by half planes or half spaces or whatever, and then this feasible region, you find a corner somewhere, and that corner is going to be an optimal solution, if there is an optimal solution. And this is how it works, even if you have 10,000 decision variables, except you're looking at the 10,000 dimensional space. But you can't draw it, so you have to compute it in a different way. So for larger problems, we will use the simplex method. And that's what we're going to learn next week. Yes? Yes. Well, you could use a matrix to do what?
To model the linear equation in n dimensions.
Yes, you could. And in fact, that's what the simplex method does. Any other questions? Okay, there's no homework exercise for next week, but we'll start again with homework afterwards.